some more challenging concepts. So I'm just going to join on a different screen so that I can write. And before we go into all the R, I want to talk about something. So while I'm pulling this up, does anybody have any questions? Any questions at all? All right, so I just joined. Okay, good. Now I'm going to be able to share my screen. Almost ready. All right, so today we're supposed to discuss comparing proportions and odds, but I want to expand the discussion to also look at the question of general linear models, okay? General linear models. And for the purpose of this discussion, I'm going to depend largely on writing. So forgive my handwriting. And mostly what I'm hoping to show you is model equations. So I'm going to spend hopefully the next 20 minutes just discussing model equations. And I hope that if you have any challenges with this key concepts that we'll be able to discuss. I know that the way that we have taken the class since the beginning, we have mostly focused on the general concepts. We have also focused on you being able to use the software. But as we transition, especially as we get to this point where we're dealing with regression, there are some concepts that we might have gone over very quickly, but I hope that you would leave this class feeling more comfortable with them. And that mostly relates to notation, okay? Notation for regression, okay? Notation for regression. And usually when we are understanding, and the reason why I feel like you need to understand the regression from the point of view of notation is because then you're going to see, as we discuss today's topic in R, we're going to see how that flexibility becomes part of how you're thinking about the regression and the analysis. All right, so when we're thinking about regression models, we would usually have, if this is linear regression, we would have the expectation of y equals beta 0 plus beta 1x. Okay, and we can make this more complicated, but I'm going to keep it very simple. And I'm going to focus on what I believe you need to be able to understand the extensions that we're going to do today, but also what I believe you need to be able to fully grasp what we're doing in multivariable regression. Okay, and this is linear regression. Can somebody remind us what linear regression is? And because linear regression, what is this variable that the outcome, what is it likely to be? In linear regression, what kind of outcome do we have? What kind of variable is the outcome? Is it continuous, binary, 0 or 1, or count? Does anyone wants to give it a shot? In linear regression, what kind of variable is the outcome? Is it continuous? Is it a binary variable, or is it a count?
Usually continuous.
Usually continuous. Very good. So in linear regression, it is usually continuous. And this parameter in the model, what we're trying to model in linear regression, is the mean of the outcome. Okay. And whenever you see this E in front of the Y, what they're really saying is the expectation, which is also the mean. Okay. Expectation, which is also the mean. So what we're really trying to do is that we're trying to model the mean of the outcome, and this is the variable. This X here indicates the variable, which is the what I mean the variable. I mean this is the predictor variable or the explanatory variable. This is the variable that is trying to explain the outcome, and this can also be the independent variable, while the outcome is also known as the dependent variable. Is there anything? I mean, I expect that you know pretty much everything that I've mentioned here today with respect to the variables. Is there anything that's not clear before I start moving forward? Anyone have questions at this point? Yes, no? I don't know whether to keep going or to make it more complicated or not. Can someone tell me what this is? Does anyone know what this is in the model? This beta 0.
That's the intercept, the y-intercept.
That's the intercept. Thank you. That is the intercept. Okay. Very good. So the intercept is what you obtain when you set everything else in the model to 0. Okay. When you set everything else in the model to 0, you get the intercept. So this intuition is important for all that we're going to discuss today in the current hour class, but also we're going to discuss as we move to talk about logistic regression in more detail in the afternoon or in the evening, depending on which country you're joining from. Okay. Now, I'll take these off so I can write freely. So that's what we have in linear regression. When we switch to logistic regression, in logistic regression, we are trying to model. So in linear regression, we're modeling the mean. In logistic regression, we're trying to model the logarithm of the odds. Okay, we're trying to model the logarithm of the odds, and the reason we're trying to model the logarithm of the odds is what we're really trying to understand is the proportion. So the question you might have is, if you have a 2x2 table, and if you go back to the context of chi-square, which we have seen, if you have a 2x2 table where some people have the outcome, yes, no. Some people have the exposure, yes, no, right? You can calculate what proportion of the individuals are experiencing the outcome among those who are exposed, and divide that by the proportion of those who are experiencing the outcome among those who are not exposed, right? And these proportions, and if you remember that we talked about in the beginning, we said that you can calculate proportions from odds, and you can calculate odds from proportions. Okay. Now, because proportions and odds are linked in that manner, it helps us when we're trying to analyze the outcomes that are binary, 0 or 1. It helps us to do that from the point of view of the odds, right? In logistic regression, we are modeling the odds, but the reason why because if you remember that the odds in the mean, right? Let me go back to the mean. We have values that go from negative infinity to 0 to positive infinity, right? Because that's a continuous variable. But in the odds, we have values that go from 0 to positive infinity, right? It will go from 0 to 1 to positive infinity. We do not have values going to negative infinity, right? Odds do not have this side of the equation. And so the odds are not truly continuous, right? And as a result, if you try to use regression models without doing something to them, it will break down. You will not be able to. And so in order for us to be able to analyze using regression models, we take the logarithm. And so we then analyze we then do the analysis using log odds instead of just odds. This is the whole point of logistic regression. In logistic regression, we're trying to conduct the analysis using log odds. And what that means, therefore, is because if you ask anybody how to interpret log odds, it's not interpretable. You have to back transform, okay, or exponentiate the results that you get in order to obtain odds ratios. Okay, so the reason why I'm giving you this discussion is so that you get all the way to the end and you understand where we're trying to go before we start running code, right? It's easy to run code, and if you don't fully grasp the concept, it's going to be hard for you to follow along. You will not know when code breaks down. You will know like what you ought to do in that scenario. So if you remember that I was just showing you the model equation for linear regression, for logistic regression, the model equation therefore is the log of this is the odds. The odds, if you remember, when we calculated, it said is the proportion divided by 1 minus the proportion, or the probability of success divided by the probability of failure. So this is what's on the left side of the equation. And the right side of the equation looks exactly the same. Okay? The right of the equation looks exactly the same. This is the logistic regression. Okay? And once you get this basic structure, it's easy to then begin to take all that we learned in linear regression and extend it, right? So now we can extend and add an interaction term because we've seen that before, right? So if you want to look at whether the exposure, and say we're looking at, because then it becomes more challenging, if you have a treatment that you've administered and you want to see whether the results for that, the effect of that treatment differ by gender, or sex, you can add interaction term. And we can also switch this right side of the equation, and we can have a multivariable regression model. Now we have three variables, okay, x1, x2, x3, and this can be whatever you want it to be. This could be, this one could be the treatment, while this could be sex, this could be income, this could be age, and this is multivariable regression. Okay, so we've essentially, in 3 slides of taking a look at this, we have gone from the intuition that we had from linear regression, and we have extended that to logistic regression. And now we have indicated that you can also take this logistic regression and complicate it further using everything that we learned in linear regression, the interaction terms, right, as well as multivariable regression. Any questions at this point? Any questions? Oh, this is perfectly understood. There is nothing to worry about. If I complicate this further, you're still following. If you want me to go over it again, please indicate. Going.
Please,
Just
please
double,
do
just
one more
double
round.
checking. Sorry, I
You
just
said?
wanted to double
Thank
check
you.
that the
Sorry, Deb.
P.
Looks like 2 people are speaking at the same time. Debbie, what did you say? I didn't hear you.
Okay, I just wanted to double check that the P in the logistic equation is proportions. Is that what you said, right?
Yes, that's proportions. Yes.
Okay, thanks. That's it.
Yeah. Sabina, what did you want to say? Sorry.
No, I said I was requesting if you could do just one quick overview.
Okay.
For, yes.
Okay. Very good. So I'm going to just write it all over as if I didn't just do that, so that you can see it develop again. We start from linear regression. We said that in linear regression, and sometimes you see this expectation of y, sometimes you just see people write y alone. But in linear regression, we have on the right side, we have the mean of the outcome, because the outcome is continuous. And that's simple. It's easy to work with because the outcome is continuous. It can be, there's the right side and the left side, both can have the opportunity to go to infinity, and they can be normally distributed, so that because of all of that, we don't need to do anything to linear regression, right? So we have a model equation that looks like this. This is the outcome, and this is the predictor. This can also be called the dependent variable because it depends on something, and this is the independent variable. This can also be called the explanatory variable because it explains this variable. Okay, and we said that if you set this to 0, you get this variable, you get this parameter, which is the intercept. Okay, so essentially, and if you remember, in interpreting this result, when I said set it to 0, for instance, if you're looking at what the number of hours worked by resident doctors, if the resident doctor does not work any hour at all, and we're looking at maybe the mean of their job satisfaction score, which is this parameter, right? So if the resident doctor does not work any hour at all, maybe they're on leave that week, the intercept will tell you what the mean will be. Okay, so this is what we had in linear regression, and we've gone over this before, so I'm hoping that you understand that. But in some scenarios, we have to deal with proportions. Okay? One of the ways that we analyze proportions, and a proportion, examples of proportions like the prevalence of something, the incidence, these are proportions, right? And one way that we analyze proportions is by converting them to odds. Okay? Remember that we said that odds are calculated from proportions as the proportion of success, or the probability of success, divided by the probability of failure, which is essentially P divided by 1 minus P. So if you have 50 people out of 100 who develop a disease, or let me say 60 people out of 100 who develop a disease, that means 40 people out of 100 did not develop the disease, right? And if someone asks you what the probability of the disease or the proportion of people who get the disease is, you have this value, 60 over 100. If they ask you what the odds of the disease is, you have this value. And you can calculate, it comes to 3 over 2, which is 1.5. Okay? That's odds. And we've talked about all that before. But if we want to analyze odds using regression, we cannot use this linear regression framework. We have to use the logistic regression framework. And as I was just alluding to, that's because proportions do not have this symmetry that we see with continuous variables, right? Proportions will go from 0 to 1. Odds will go from 0 to infinity. Okay? And so we need to be able to do something that allows us to have this symmetry, because without symmetry, you cannot be normally distributed, which will affect which means that we cannot conduct regression. So to be able to do that, we take the log of the odds. Okay? And so now with log odds, we can use something called logistic regression. Okay? And essentially what we're doing is we're only swapping out the outcome from the linear regression, from what we had in the linear regression model. So we can have something that looks like this. The probability or the proportion, 1 minus P, and then the right side of the equation looks exactly the same. Everything else here is the same. This is a predictor, an independent variable, and if you set this to 0, you will get the intercept. But this in the bracket is the odds, and we're taking the log of those odds. This is just for you to understand what is going on. Obviously, you're not going to calculate this by hand, right? But you need to understand what is happening in the back end. All right. And I also then said that we can extend the logistic regression just like we did for linear regression. We can extend logistic regression equals beta 0 plus beta 1x. This is what we just saw. But you can switch this and have, keeping the exact same left-hand side of the equation, you can switch this, and now you have an interaction term. So where this was maybe treatment, so let me say this was treatment, okay? No interaction term. And we can switch this. If we're interested in looking at how the effect of treatment varies in men versus in women, we can add an interaction term for sex, where maybe female is 1, male is 0. Okay? This is interaction or effect modification, depending on if you heard it from statistics or in epidemiology. We can also complicate this further by adding other variables. Instead of just a variable called x, now we have multiple variables called x1, x2, x3. This is multivariable logistic regression. And an example of this actually in real life will be where we write beta 0, but maybe in the first, we're looking at the effect of treatment, and then we're adjusting for sex, and this becomes 2, and we're adjusting for maybe income, and we're adjusting for maybe, what else? Age, and we're adjusting for, and we can continue. But this is the fundamental premise of multivariable logistic regression. Any questions?
Thank you. I think I've now gotten it. So as an example for the multivariable, if we use the data set for the mental health for healthcare workers, maybe we used okay, I've forgotten the exact tools, but I remember I think in our case we've ever used PHQ-9 and GAD-7, and then we have now the social demographic, so gender, number of hours worked per week, and so on.
And so on. Yes, precisely. So those will be these additional variables that we're adding to adjust so that we can control for and ensure that we're getting an effect that is not confounded.
Okay, thank you. I've gotten it. Thank you.
All right. Any other questions? Because I'm going to switch over and we can now look at the actual R. All right, so I'm still going to come back and continue this writing, but let's go to R first and ensure that you actually get the logistic regression before we complicate it by bringing additional forms of additional analytic approaches. Okay. So I'm going to stop presenting, stop sharing my screen here. And okay, excellent. So we had looked at chi-square, so I'm going to skip over the code for chi-square and just jump straight into logistic regression. And now I'm looking at it and I realize that we only have one example, and we can play around with it a little bit, but we only have one example in the code. In logistic regression, as I was showing you, you will have the outcome and you will have the exposure or indicator variable, right? And you're going to call the data, but pay attention to this side of the model. First of all, this is a GLM, right? This is a GLM code or GLM function. And if you go back to linear regression, we said that you could actually model this using GLM or using LM. But that GLM gives you more flexibility. You can layer upon it other things. And you'll see that today. In logistic regression, the outcome has to be a binary variable 0 or 1. Right? So you will code it such that 0 or 1, and you have to code the aspect that you're interested in as 1 and the reference as 0. Okay? And then the right side of the equation, it does not matter. It can be continuous, it can be binary, it can be categorical or a factor, and you can do multiple different things. All right. So let's go ensure that we have the data loaded. Set does not exist in my working directory. But it does though. Okay, I see the issue. So I have it as an XLSX file, and it's a CSV file in the code. So I'm just going to modify quickly, and then we can carry on. Do we have any questions at this point?
Just clarifying, you say we should code the outcome variable of interest as 0, as 1.
Yes, you should code the outcome of interest, the direction of the outcome of interest as 1. Yes, absolutely.
Okay.
Yeah.
Okay. Thank you.
Yeah. All right. So now I'm going to load the CSV file, and as usual, always want to open the file, take a look at it, make sure that the variables look the way that they should. We have age, we have mental health score, we have the job satisfaction score, we have workload score, right? And we have hours worked. So we can see the hours worked goes from 30 all the way to 100, right? And we have married 0 or 1, we have age category. So now let's go back to our code. First, we create the binary variables for hours greater than 80. We've seen how to do this before. This is one way to do this. And because we didn't call the dplyr library, obviously it's up here in the code, but I didn't run it. So that's why it's giving us this error. So this is one way to create the variables. I like this because you can clearly see this is the if-else function. And I always want to identify what the NA is and make sure, because in a lot of times, if you a lot of times there's missingness in the data, right? So make sure that you always, first of all, tell R how to treat the missing levels, and then you figure out exactly what you want to code. So here we're saying that if hours worked is greater than 80, we want this variable hours greater than 80 to be assigned 1. And if it's not, we want it to be assigned 0. So we're interested to see whether those who work more than 80 hours have, what their job satisfaction is, what their mental health score is. And we also create a variable called severe mental health. And in this case, we're using the mental health score greater than 20. And if the mental health score is greater than 20, we ask it to assign 1, otherwise 0. So now we run this. And we could do a cross tabulation, which allows us to see exactly what to expect. This is what the 2x2 table would have looked like, right? At least part of it. And here you can add 13 plus 16, you can add it across or downwards. But this is what the basic 2x2 table would have looked like. Okay, so sometimes you can create a version of the variables that are labeled as, in an informative manner. I like to do this, make life easy. So I'll have 2 versions of the key variables that I'm working with. Another way to do this would have been to create variable labels. So both approaches are okay, but you should just know exactly what you're doing. All right, so I'm skipping over the chi-square because we've done this before. Now, back to the logistic regression. We have created severe mental health, as an outcome 0 or 1. And we have hours worked, which is a continuous variable, right? And we've called the data, but I was saying that you should pay attention to this side of the code. There's two functions or two pieces of information that we're giving R. We're saying to R that the outcome is a 0 or 1 variable. Okay, that's essentially what this binomial distribution is saying, that the outcome is a 0 or 1 variable. And we're also saying to R that we're looking for it to treat this as the log odds. Okay, and that's what the logit means, the log odds. So we're calling the family, telling R that the outcome is a 0 or 1 variable, and we're calling the link, telling R that we want you to treat this as the log odds. And we're saving this variable, this model, as model 5a so that we can call the summary, we can do some more things about with it, but this is what it looks like, very simple. Okay, so when we run that, we get results that look like this. When you look at the R output, it will first of all give you the call, and then it would list the coefficients, right? And this estimates, these are the beta estimates, and the standard error gives you the variance and the p-values. What is this 4.60656 in the regression equation that we had seen before? Does anyone remember?
That's the intercept, B naught.
That's the intercept.
Beta naught.
Beta naught, excellent. So that's the intercept. And this is beta 1. Okay, this is beta 1. And this is beta 1 telling us what happens for every 1 unit increase in the X, which is hours worked. For every 1 unit increase in hours worked, severe mental health, the odds of severe mental health changes this way. But because this is the log of the odds of the, right, we have to exponentiate to be able to understand what is happening. Obviously, we can look at other parts of the summary, you know, the standard errors, the z-value, but the p-value already tells us that this is statistically significant, right? We can look at all these other, the residual variance, the AIC, but those might not be giving us much information because this is because this has only one covariate, right? This is a simple logistic regression. Okay. Now, this code shows us how to exponentiate. We're essentially saying that in that model 5a, extract the coefficients, okay, and extract the confidence intervals, put them together in a table and exponentiate. Will this work? Yeah. So this is what it looks like. Another way that I would have liked to do this, I like to build this simpler, will be to bind exponentiate the coefficient model 5a and exponentiate, ask for call the confidence interval model 5a. I like to use this second one. It's easier for me to see if there is what is the expected it's supposed to be okay. I know in this way I'm calling the exponentiate twice, but I feel like I'm actually seeing the flow easier. So any of these approaches works, but here we can see that the odds ratio is 0.9597396, and the lower limit of the odds ratio, with lower confidence interval 0.93, and then 0.98. Okay, so this is logistic regression. Can someone tell us how to interpret this odds ratio of 0.96? How would you interpret odds ratio of 0.96? Anyone wants to guess? We will say that, and I'm going to type this. I hope this is large enough on the screen. We will say that the odds of severe mental health is 4% lower for every additional hour worked by resident doctors, healthcare workers, whatever you want. Why did we have 4%? Anybody wants to guess? Why is it 4%? We've seen this before. We talked about this, I think, in the last class. Because it's 0.96, okay? 0.96. And the way that we interpret odds ratios is if the odds ratio is less than 1, we will say if odds ratio is less than 1, we will subtract the odds ratio from 1. And that's what we did here. So 1 minus 0.96, which gives us 4%. Okay? It's 0.04, which is 4%. If the odds ratio is greater than 1, or let's say between 1 to 2, we have two options. We can subtract 1 from it and then report in percent, which is basically what we did here. Subtract 1 from it and report in percent. So an example would be if we had an odds ratio of 1.7, we could say that this is 70%, but then it will be greater. Okay, 70% greater. So that's one way. But the other option that we have is to report it just by reporting the odds ratio by itself. Okay, we could say, or 1.7-fold greater, using that 1.7 example. Okay, so this would have been 70% greater or 1.7-fold greater, or 1.7-fold. So that's one way. But if the odds ratio is greater than 2, then we will only be able to use the fold. So we'll say 1.7-fold greater, or maybe 2.7-fold, because now this is greater than 2. So that's how we would interpret the odds ratio. But I want to do something else. So I want you to pay attention to the fact that this is a continuous variable. Okay, this is a continuous variable. And because this is a continuous variable, we are only we have to say for every additional hour worked, or for every 1 unit increase. All right, so I'm going to write a different model. I'm going to run it, and I'm going to ask that someone volunteers to interpret. Okay, so let's see. I just want to copy. All right, so let's call this 5B, and then change this to hours greater than 80. Remember that hours greater than 80 is a 0 or 1 variable, right? Or we could even say, use this one, hours greater than 80x, which is more informative. And so when we run this model, we get results that look like this. Okay. So take a careful look at the results. And now I want to also copy the code to exponentiate. The reason I'm copying this code is so that you can know that you don't have to cram the code, right? You just have to look for the code. All right, so now we have odds ratio of 0.29. How would you interpret an odds ratio of 0.29 for this question, right? Hours work better than 80 hours. And the outcome is mental health, is severe mental health. Score or whatever. All right, anyone wants to give it a shot? So hours were greater than 80, and the outcome is severe mental health, maybe illness or severe mental illness, based on the mental health score.
Can I try?
Yes, please.
So I think it means that there is a 71% for every our increase in work, there's a 71% lower chance.
Okay. 71% lower chance, yes, that part is correct. But is it for every hour increase? Remember that we're comparing those that work more than 80 hours versus those that work less than 80 hours.
Less than.
Right, so what's the reference here?
The reference is hours work less than 80 hours.
Yes, very good. So that means when we interpret what we will say that 71% lower among those who worked
71 hours less.
No,
71
not
hours more. Sorry. 71 hours
80 hours more. We're dealing with 80 hours, right?
Sorry, 80 hours more. Sorry.
Yeah.
So there is 71. Yeah.
Go ahead. Let me write it out so you can see. So the odds of severe mental illness, don't go, is 71% less, right? Is that what you want to say?
Yes, 71% less.
Among those who worked more than 80 hours, right?
Yes.
Compared to those who work 80 hours or less. Does this represent what you were trying to communicate?
Yes, among those folks, 80 hours, over 80 hours compared to. Yes, this is what I wanted to say.
This is what you want to say. Okay, very good. Does anybody disagree with this? Does anybody agree with this? If you agree with this, can you raise your hand or speak up and provide some support. Okay, I see Brandwell. Okay, I see Wanga. Is there anyone who does not understand what she's trying to illustrate here?
Okay, I understand what is illustrated, but is this okay? Is it true? Because I would have expected the opposite.
Okay, all right. So this is true. This is correct. This is the correct way to interpret. Remember that we highlighted remember that the reference is those who worked 80 hours or less. That's the reference. So that's what we're comparing to. Okay. So when the exposure is continuous, like in hours worked, the first variable we saw, right? What we're comparing to, we're comparing for every additional hour, or for every additional unit increase. So that means if you go from 0 to 1, or 1 to 2, or 2 to 3, or 3 to 4, okay, that's what's happening when the exposure is continuous. But when the exposure is binary, R is assuming that you're actually going from 0 to 1 and it stops there, where 0 is the reference that you indicate. And when the way this variable is written, hours greater than 80, where more than 80 hours is what we're interested in, then the reference is less than or equal to 80 hours. So it means that it's only going from 0 to 1 and it stops there. So we could have done this differently, and maybe that would have helped. You see, we could have done this differently, where rather than use this form of the variable that it would just have been hours greater than 80, which is 0 or 1 variable. And if you run that, you would have gotten the exact same results as what we get here, right? The exact same results. But we chose to use the greater than 80x because that's more informative. We can see here it is assuming that because we have queried from 0 to 0 or 1, it's going from 0 to 1. The 0 is the reference that we're comparing to. The 1 is what we're interested in. Okay? So that's basically what's happening here. Okay? So the variable that we're interested in, sorry, the form of the results that we're interested in is for those that are greater than 80, and we want to compare to those that worked 80 hours or less. I don't know if this has helped you clarify.
I think so, yes.
I think so. Okay. All right. So I think there's a hand up. Okay, Wanga, please.
I have a question. So if this is 0, what would happen if we are expecting the negative of that, such that it's not moving from 0 to 1, but rather moving, like, would it move from 1 to 0? Like, would R be able to show us the opposite?
No, it will not go. So the way that, so if this were continuous, as we saw earlier, it goes from, this can go from -1 to 0 to 1 to minus, like this, because if it's a continuous variable, it's just one additional unit increase. But it is always an increase. It's always comparing the lower to the higher. For this one, where it's a binary variable, binary meaning there's 2 levels, right, as you know, and the R will code it expect that you're coding it as 0 and 1. So there's no negative when it's a binary variable. If it's a continuous variable, it can be negative. You can have -5, -4, -3, -2, and it would increase from -5 to -4, then -3 to -2, right? It doesn't matter where along the spectrum it is for continuous variable, right? It can go from 1000 to 1001. It's always 1 unit increase. Okay, but for the binary variable, it only expects 0 and 1. Or if you label it differently, like we did for ours greater than 80, we have 2 forms of the variable, and we see that the results are essentially the same. It is expecting 0 or 1, and the 1 is the form of the variable that we're interested in, and the 0 is the level of the variable that is a reference, right? And that's essentially what we've also seen here with when we had this form of the variable with the x at the end. There's a level of the variable that we're interested in, which is those who are greater than 80, and there's a level of the variable that we're not interested, that is the reference, right? We're also interested in it, but it's the reference. So I hope that explains the question about negatives.
Yes, it does.
Okay, excellent. Any other questions? Okay.
Yes, I have a question. Please, what is the name of the file that we're going to run for this hour? This today's topic. What name are we supposed to run on our lab 5?
Yeah. You don't have it?
Okay. I don't know if you have the link. Like, where can we go to get it?
It could be in the Google Classroom.
Okay.
If you're not able to get it, we can try to share it.
Okay. Let me try and get to the classroom first.
All right. So this is basic fundamentals of like simple logistic regression. And now we can, like, you remember when I was writing on the iPad and we said that we could add in other variables. We could add interaction terms. So I've shown you 2 things with the logistic regression. I've shown you the basic form when the continuous variable is the exposure. I've also shown you the basic form when the binary variable is the exposure. So before we move on, let's look at other forms of the variable so that you leave without with clarity, so to speak. So look at this variable, the number of children. It's a continuous variable. Okay, it's not a continuous, it's a count variable. So we have 0, 1, 2, 3, and it goes all the way to 6. We can model this variable. I'm going to factor. Okay, so the first thing we want to do is take that number of children and convert it to a factor just for convenience, so you can see this. Yeah, please ask your question.
Okay, yeah, I checked the classroom. It looks like I'm seeing R lab 4, but I couldn't see R lab 5.
Okay, does anybody else not have access to R lab 5?
R lab 5 is in the comments now.
Okay, they've posted it. Okay.
Thank you. All right, so I want to modify the number of children, so I'm going to create a new variable. So this is one way to do this, right? I'm going to create a new variable, and like I said, you should always indicate the n, what you're asking R to do. So I'm going to ask R if the number of children is 0, to call that no children. And if the number of children is otherwise less than 2, so let me say less than 3, to say 1 to 2 children. Okay, and then if the number of children is otherwise less than 5, to call that 3 to 4 children, and then more than 4. Okay, so now we have this new variable that we're asking how to create. When we're modeling the factor, there's a number of things that we can do. We could have taken the children and ask R to treat it as a factor. Okay, I don't know why it keeps popping up this. We could have asked R to treat it as a factor. Now, when I run this, why is it giving me all these warnings? Debbie? Yeah.
Oh, I have a question. In
Yes.
the last line of code, you said if children less than 5. So what happens to situations where somebody has 6 children? Is there such in the data set where persons have 6 or 7 children? Would this line of code account for those? Because it says if children less than 5.
Yeah, very good question. So the way that if-else functions work is that you have the true and then false. So the way if-else function works, just like in Excel, same way in R, the same logic. If-else, you say what the condition is, then you say what it is if it's true. If it's not true, then you say what it is if it's false. Now, because we're building this over multiple levels, that's why you didn't really pick it up. What we're saying here is that if this is 0, if there's no children, it should say no children. But what that then means is that there's something missing on this side, which is when there are children. So when there are children, we are then asking it to take some more steps. So on this side, what is implied is there is something on this side. But instead of specifying it, we move it to the next line and we call another logic and say that if there's less than 3 children, i.e. 1 and 2, indicates 1 and 2. And then here we say if there's less than 5 children, among those who do not already meet all these conditions, okay, then we say 3 to 4 children. That's less than 5. But notice that there is another entry here, which is the greater than 4. So anybody whose kids are 6, 7, 8 will be captured under the greater than 4. So this is the full flow of this logic. All right. So now when we run this, I have not used this variable yet. I just created it. Here we have factor is children. So we've asked R to treat the variable children as a factor. So we can actually see for those who have 1, 2, 3, 4, 5, 6. What happens to those who have 0 children? Does anybody know? But if you look in this data set, there are certainly people who have children, who have 0 children. Yes.
Okay, I have a question. Sorry, I tried to run the R, but I'm experiencing an error in my in this. I don't know if I can get like a help. It's showing me error in RDS on percentage. Could not find the function.
Do you have the library dplyr loaded?
The library what?
Dplyr.
Maybe I can share my screen because I don't even know
Okay.
what that means. Yeah.
Sorry, guys. This is a quick detour.
Yeah, sorry guys. Let's see. Okay. I don't know if you can see my screen.
Yes. Not yet.
Okay,
No.
so
Yeah. Okay. Now I can. Yes.
okay,
So
yeah,
go
so I
back up.
did try.
Go back. Hold on. Go back up. So you still have this set. The working directory is set as if you're using my computer.
Okay.
So first of all, take out that set working directory line, or put a hash in front of the line. A
This
hash
year?
tag. No, in the front, in front of the whole line, in front of set working directory.
Okay.
Yeah, put a hash there so that you
A
comment it
hash.
out. Yeah.
Hash, okay. Uh-huh.
Okay. Now go back to session at the top of the screen.
Session.
So at the top of the screen, you see session. Click session. See set working directory.
Okay.
Set source file location. Click that.
Okay.
Now, do you have the resident doctors file?
Yeah.
Do you have it saved in the same place where you have this file saved?
Yeah.
Okay, very good. Now, scroll down. Oh, you already have RDS loaded even. So run your library dplyr.
Where will I
So
run that
you
from?
go to line 17.
Okay.
So you see that chunk of code, run it.
Oh, okay.
So you see this type function, not 0, percent greater than percent. In
Percent.
the console, the error that you have.
Yeah, the error,
Yeah, so that error, percent greater than percent, is the pipe function. That's the pipe, PIPE.
Okay.
And what it is useful for is for you to add lines of code to each other.
Okay.
Right? And so for you to be able to use that, which is essential in data management, you need this dplyr library, which is one that's in line 17.
Okay.
That you just ran. Now go back and run what you were trying to run.
Okay.
Which I suspect is the children, right? The children.
Yeah.
Yeah. Okay. So run that again. Let's see.
Error again.
So it says that RDS but you do have the file.
Yeah, I have it. That's the file. Like, this is the RLab 5. This is resident doctors.
Okay, can you open the file? Let's see.
Okay, that's resident doctors, right?
Yeah, the RDS. No, open this RDS, not the resident doctors.
Oh,
The
okay,
RDS that
RDS.
you have in your environment.
Yeah, let me look for it.
No, you have it right here in the environment where it says data.
Oh, okay, yeah.
Yeah, open it. Let's see. You should have a variable called children. So first of all,
okay.
can you move your screen sharing? So you see that. Okay, so here's the thing. I should note that the versions of the data sets have changed over time. And I just picked the children that I have in my file, and that's why the way children is spelled in your version of the data set it's in caps.
Okay.
So can you move this? You're sharing your entire screen, move it away where it says stop sharing, move it out, or minimize it.
Okay.
Right, so you see children?
Yeah, children.
It's in capital letter, right? It's all caps. So you need to edit in your file to fit that.
How do I edit it here?
So go back to your code.
Code.
So no, go back to our lab 5.
Okay.
Yeah, so scroll down to where you have children. So where you have children, now you have children written as small letters. You need to change that to capital.
Here?
Yeah, everywhere in that. Another thing that you could do is just reset it. But just edit. I think it's better to just edit it, children.
Okay, so I should just put everything capital.
Yeah, and it should run.
Okay. Okay, so this part is I've put it in capital. Then let me try it again. Let's see. I try it again.
So it does run. That was the problem. So
No, is that not error I'm seeing? Like
that's the old error.
this thing is this not error I'm seeing?
It's
Okay.
the old error.
Okay.
Yeah.
So where's this thing? Okay, is it this one? Like how did you where will I see where it ran?
No, because if there's an error, right, you'll see the error in that or just under the source code. But also, if you go in the console, you'll see that the error is not showing under the code that you ran.
Oh, okay.
Right. So if you scroll back up in the console, not in the code, in the console on the lower left quadrant,
Left.
right? Scroll up.
Okay.
So take that scroll, this scroll it up slightly, not too much. You've gone too fast. Yeah. So you see that when you had the error you had, the code is on the under it, showing up under it. But if you scroll down to the bottom now, you'll see that there's no error under it. So that error is not for the code, it's not for the updates that you've made.
Okay.
Yeah. Okay. All right. So let's jump back into the class.
Okay. So like everything is fine now. Like I can like just continue.
Yes, you can just continue precisely.
No,
Right.
no, sorry, there's still error. So sorry, don't be angry. Like I'm still seeing error. I don't know, like I looked at this one, model 15C.
So I'm going to stop sharing so you can reshare your screen.
Oh, okay.
So we haven't gotten to that point.
Okay, you've not gotten there.
No,
Okay.
not gotten to that point. And it's very likely going to be the same kind of problem, right? That the code that you the data that you have and that the variables are edited differently. So you just check the variable like children, hours work.
Okay, like that files I clicked on. Okay.
Yeah, exactly. So make sure that the variables are edited, written correctly, and that should be fine.
I've checked it. I don't know. Can you see my screen?
Yeah, but I can see your screen. So here's what you have to do to check. Can you go back to the code?
Yeah, let me
No, go back to, I can see the data.
Yeah.
Okay. And you can see the variables. Look at how they're written.
GHQ score, job satisfaction, workload, age, dist, marital status, children, female.
So now go back to your code in the R Lab 5.
Okay.
For each variable that is listed in that code, you will need to make sure that the variable is correctly spelled in the data set. So that's not something that you will have to do while we're continuing with the class.
Oh, okay. Okay, let me try it and I'll see if I'll have problem.
Okay. All right. All right. So Over the last few minutes, we have talked about so we have talked about logistic regression. We looked at simple logistic regression using a variety of approaches. We looked at simple logistic regression when the predictor is continuous. We looked at when the predictor is binary. Okay. And now we've also looked at when the predictor is a factor, right? And I was just going to ask somebody to tell us so here we have children 6, 5, 4, 3, 2, 1. Where's 0? I was going to ask someone to tell us where 0 is. What happens to those who have 0 children?
Well, 0 is the comparator, so
That's the comparator, yes. Or also
it's
known as
not there.
It's not there.
Oh, it's the intercept.
It's the intercept. Okay.
Sorry, it's the intercept.
Yeah. And so that means that if you set all of these to 0, then that's what you get. But then for each one, you will have to compare each one to the intercept. So essentially, you will have to compare 1 to the intercept, 2 to the intercept, 3 to the intercept, so like that. Now, because we have a small data set and there's not a lot of people who have 4, 5, 6 children, that's why you have these huge standard errors. Okay. And that's why I first changed, I created a new variable, and we can call it children cat, we can call it children X, or whatever we choose to call it. This variable might be more informative than if we had just used factor by itself. So let's try that and see what the results will now look like. Okay. So if you look at this now, the intercept is still very large, but if you focus on the standard error, all of this plus 0, 0 means that there is nothing, and it's only adding them because of this intercept that's very small. But when you look at these estimates and the standard error now, that's huge standard errors that we're having, they have gone away. And in this case now, we now experience a new problem. You know, previously, R, and I think that I showed the fact that I keep, let me do this differently. So factor children, I want to keep it up so we can scroll up and you can see the problem that I want to highlight. I'm just asking it to silence the warnings. I don't want to deal with them. All right. So here it automatically chose the intercept for us because the variable had 0, 1, 2, 3, 4, 5, 6. But here we have a scenario where no children is not the intercept. But this is not what we're interested in. We want no children to be the intercept. If we had written this as 0 children, you might not have realized because it's ordering them in alphabetical order, right? And maybe if I had said this is 4 more than 4. So now, when I wrote it like this, we didn't see the intercept was automatically chosen the way that we would have wanted. We want 0 children to be the intercept. But if you go back to what I had what we had encountered where no children is the intercept. It means that we need a way to choose the intercept. We need a way to choose the reference for R, right? And there's code that we would use that will specify the reference that we're interested in. Okay? And relevel is one of those. If I remember it correctly, so now we're telling R that this is the reference we're interested in. And so when you run this code now, it says it's not fine. Well, because I didn't add this here. When you run this now, it should select a level only for unordered factors. So there's got to be a different function that would allow us to choose the variable. So I will find it and I'll let you know. But essentially, we have to be able to indicate the reference level. I haven't done this in a while, so and then we will automatically just generate, and it will just give us what the correct level is. Someone's hand is up.
Yeah, good afternoon again. I
Yeah.
wanted to ask, how does R automatically choose? How does it automatically choose the reference level? Is it the first level you have assigned, or it just randomly chooses any level on its own?
Yeah. So R will usually just do it in maybe alphabetical order. So that's why when I wrote this as 0 children and this as more than 4, R chose 0 children, because if you order this in alphabetical order, comment this out. If you order this in alphabetical order, then R automatically chose 0 children, because 0 children is when you're ordering in alphabetical order, you start from numbers, the smallest number, and then you go to the letters. And, so that's one way that R chooses the alphabetical order. Okay. So you can choose the way that ideally you should select the reference is 2 ways. One is which one is most informative, and that depends on the study. So if you're doing a study where you're asking about you're doing a study of BMI, okay, where you're looking at the relationship of maybe gender and BMI and trying to wonder what kind of study that might be. But if for BMI, you would want, very often we like to use the normal BMI as a reference. So if you remember what BMI categories are, there is underweight, there is normal, there is overweight and obese, right? Underweight, normal, overweight, and obese. So we wouldn't use the underweight as a reference, even though it's the lowest value. And we would not use obese as a reference, even though when you order it in alphabetical order, no, actually in alphabetical order, you will choose normal weight. But we choose normal weight because it's informative, because that's the one that we're trying to compare everybody to. So that's one way, the one that's most informative. The second way is the one that is most prevalent, the one that has the largest number of people. And the reason that helps is if the levels start breaking down, you know, like we saw earlier with the number of children, the levels that don't have many children will have wide standard errors, right? 4 doesn't have many children, 5 doesn't have, and as you can see, there are more people with 4 children than there are with 5 or 6. And so the standard error for 4 children is less than the standard error for 5, less than the standard error for 6. But compare that to the standard error for like 1 child or 2 children. So we want to choose a level that by itself will not inflate the standard error. So if you use 6 as your reference, all your standard errors will be large. So you want to use a level that will not inflate the standard error. And so you want a level that has a large standard error. Okay? So that's how you will do it. Another way that you might do this, okay, so let's talk about this factor thing carefully so we can clarify. All right. Choosing reference. So I said that you can either use the most informative, and this depends on your understanding of the subject matter, or most prevalent. If you don't choose for R will use either, it would use the first one, okay? The first level, or it would use alphabetical order. So if you look here in this, so if you have this factor that we have for children, CHLX, we can reorder the variables such that, so we can use relevel if it's an ordered factor, but that's not what this is. So we can use something else. And what we can use, we can ask R to specify the order in this way. You have to make sure that you're labeling this correctly. Okay. So now we have to use this one. So let's see what happens if this runs. So now when we run this, so it means that something is wrong. Okay, this is wrong. We have 1 to 2. We have 0 children. Which I want to use no. So 1 to 2, 3 to 4, more than 4. Let's see. All right, so this is what you get. So this is now correct, the way I want it to look. Those with no children is the intercept. 1 to 2, 3 to 4, more than 4. Any questions? And I want to move more quickly. Any questions? No? Okay, good. So that is logistic regression, simple logistic regression. In multiple logistic regression, or what you might also call multivariable, what we're really just doing is that we're adding other variables into the model. And you saw that when I was writing by hand and showing you the beta coefficients. All that you need to do is add in these additional variables. Just make sure that it's the right spelling. And so when you run this model, the summary looks like this, okay? It looks exactly like this. And children here is treated as if it is a continuous variable, but that's not true because it's not really a continuous variable. So we can ask it to treat it as a factor. Okay. And so now it will present the results differently. You'll see just the way we had seen up there. It will break it all out, 1, 2, 3, 4, and now 0, it's its reference. Age is treated as a continuous variable. So for every 1 unit increase in the age, female is coded 0 or 1. And so as you go from 0 to 1, right? It's a binary variable. Any questions? Okay.
Oh, yeah, sorry. I'm still having issues in that section. I tried to do what you said, but it didn't work out. This exactly this place like you're talking about, like this is where I'm kind of stuck. So I don't know if I can get help at any point you're ready.
Okay, so here's what we should do. Let's advance through the rest of the material and then I will talk with you after, okay?
Okay.
Yeah, so that way anybody who wants to drop off can. All right, so for multiple logistic regression, you will add these variables in, and there's some additional steps that you will need to do to choose actually which variables you want to add in. And I don't know if we talked about this when we're dealing with linear regression, but we will usually we'll usually explore different forms of a variable to determine which one most likely fits the model that we're dealing with. So for children, for instance, we could have examined children as a factor variable like we saw. We could have examined it as a continuous variable. There's multiple different forms because of the way that the number of children is an integer. And if you wanted to just have R make that decision for you, right? You could have the same variable in the model in multiple different ways, making sure that everything else about the model is the same. But you're making only this one change, right? You're modeling it in different ways. Now, if you do this, run this again. So if you do this, now you save it as model 5C, you can have the AIC, the Akaike information criterion, choose the ideal model for you. Right, so here we're comparing model 5A, 5B, 5C, 5D. I don't think that's what I want to do. I want to only compare 5C and 5D. So if you compare model 5C and 5D, you can choose which form of the variable is best. And here you see that there's not much difference. Who can remind us what the rule of thumb is for how much different the AICs have to be for us to care? So here we're seeing that the AIC is different by 2 points, 146 and 144. Is that enough for us to care, or does anyone remember? For the AIC, the threshold is 10. If this was 146 and this was 120, then we would have gone with this model C. But because this is only different by 2, we won't care. We'll just assume that there's not much difference in the models. So that's how we will choose models, okay? And that's why we'll choose which form of the variable. And there's a longer discussion that we can have regarding how to choose covariates to add in the model. And maybe we can plan for a future, maybe next week, potentially, we can have a longer discussion regarding how do you choose these variables that you add in the model. Okay, but we've already spent more than 90 minutes in today's session, so I don't want to prolong this much longer. But in terms of selecting the model, we can use the AIC, we can use the log likelihood, right? This calls this library, and for the log likelihood, you have to view the log likelihood for each variable, for each model separately. So let's do C and D. Or you can ask R to essentially compare the log likelihood for you. So if you compare C and D using this LR test function, it will give you a p-value. Okay, it will give you a p-value. So what you were doing here is that this log likelihood, these are chi-square values, right? You could have subtracted this by hand and then go look at it in the table, but you can also ask R to do it for you, and the p-value is 0.49, which tells you that those two models are not much different from each other. All right, so I'm going to stop here. Next week, we will have a longer discussion on how do we extend the discussion about logistic regression into other models that use the proportions and odds. Okay, those models are increasingly, you'll encounter them in papers, and the way that we interpret them is different. But I also want to have a longer discussion on how do we select the variables that we include as covariates, because that is a key gap that I realize that a lot of people struggle with. So for that, would likely need to write up new code, or maybe we'll do it live as we're going, but I'll decide. And then we'll have that discussion next week, and then the subsequent week we'll do survival analysis and Cox proportional hazards models, and then we'll wrap up the class. Any questions? Any questions? Is this perfectly well understood? You feel happy that you joined today's class, or did I just confuse you?